Ladies and gentlemen, the second talk of this course will be about statistical thermodynamics. You know what is motion of molecules. You can imagine it as a movie. Molecules change in time, and what you watch are individual frames, configurations of molecules. Then, if I have motion of molecules during a long time, I can say, okay, this corresponds to a system I am interested in, let us say water. But I can do it in a bit different way. I can take the individual configurations and calculate their probabilities. Thus, I don't need the motion. I need only a set of configurations, and still I'm able to study a lot of interesting properties. And this is the approach of the so-called statistical thermodynamics. You can imagine that all possible configurations that we have are averaged in time. What I see is something where I don't see individual molecules. I only see properties of matter. And there are two approaches to these properties, either using the real motion of molecules or using the rules of statistics, of statistical thermodynamics, that is, probabilities of different configurations, and so on. The first example of statistical thermodynamics will be extremely simple. We will derive the ideal gas equation of state using very simple reasoning accessible to high school students. We will assume that we have a box with molecules, and our molecules will be very small. They will be essentially point masses. So that such a molecule in a box goes along a straight line, and it can reflect from the walls. Something like this approximately. Here you can see that the molecules once a while hit each other, so I will assume here that there are only a few such collisions. I will neglect them. So let's have n molecules, each of mass mi, and they are in a cube of HL. Each molecule has a velocity, it's a vector. If a molecule hits a wall, let us say here this wall, that is y and z, because I don't have z here, I will assume that it will reflect elastically. It means that its velocity components in the axis of that, in the x-axis is reversed, that's opposite sign. So, for example, this is this molecule. Here it's reflected, then it goes back, and again. So the question is, what is the time after which it will hit the same wall again? Well, it may also hit here other walls, so it actually can go something like here, but it's not important here. We are interested only in collisions with one selected wall. And this time after which it goes back is 2L, because it must go there and back, divided by the velocity. Well, you perhaps remember from the course of mechanics that force can be treated as a change of momentum in a unit of time. And the momentum of a particle, it's a point mass here, is its mass times velocity. So if a particle hits a wall, it changes its momentum. It changes its momentum by, because this goes to the opposite one, twice the mass times velocity. That is twice its original momentum, and here it's in the x direction. The average force caused by impacts of one molecule on one wall is then force is the change of momentum in time, that is, this change of momentum divided by that time. So I put all parts this into this formula, and what I get is mass times the velocity squared divided by L. This is the h of our cube. If it looks like the kinetic energy a bit, so you get it correctly. But let's proceed. We have force. Pressure is the force of all molecules that we have divided by the area. So I will sum up all forces in this direction, that is, it's on one wall, sum up all and divide by the area, which is L squared. So if I insert this here, I'll get this sum of over all molecules of these quadratic terms in velocity divided by L cubed, which is the volume indeed. The kinetic energy of one molecule is quite similar to this, but I must take care about the components, because a velocity of a molecule in general is a vector. So the kinetic energy of one molecule is here. I can write it like this. Here it means exactly the absolute value of the vector, and I have it squared, and this is the sum of overall components. So essentially I have a factor of 1/2 here, and 3 times something like this. I will assume that all directions are equivalent. Okay, so once again, the kinetic energy of my system of molecules is 1/2 of the sum over all molecules, mass times the velocity squared. Assuming that all directions are equivalent, I can use here just one component, and here I have 3 times this. And the kinetic energy is essentially the internal energy of our monoatomic gas, because I don't have anything else where the energy could be stored. I have only the kinetic energy. And from the formula I derived here, I just use it now. I'll get that pressure is some factor 2/3 times the kinetic energy over volume. At this moment I can put the volume to the left hand side, and what I'm getting is that the product of pressure times volume is 2/3 times the kinetic energy. It looks like the ideal gas equation of state, only I don't have temperature yet. But I have used only mechanics. I don't have temperature in mechanics. It's a concept of something else. And what I'm getting here is exactly the relation between thermodynamics, temperature, and mechanics, that is kinetic energy. That is, in other words, temperature is a measure of kinetic energy. And to summarize, I used the assumption that pressure is given as average impacts of all molecules to a wall. I have many molecules, so I don't feel individual molecules, I just feel pressure as the average result of such impact, and I used the classical mechanics. And what I got is the equation of state of ideal gas and the relation between kinetic energy and temperature. Okay, so to repeat it, here is the equation of state. It can be expressed using the Boltzmann constant instead of the universal gas constant. The relation is given by the Avogadro constant. Here is the relation, the number of molecules is a mole number times the Avogadro constant. So this is the equation of state written in that, or in this or that way, it doesn't matter. And also I got another equation, the equation for the internal energy, which equals the kinetic energy. And here is the factor I have. Essentially what I derived was something like this, only I use the relation between the Boltzmann constant and the gas constant here, or it's written also here. These constants are nowadays defined, that is essentially 1 Kelvin is related to the unit of energy. Here is the definition, and the same is for the Avogadro number. So now we know that the universal gas constant is exactly this. And a few notes. This is the equation of state. You perhaps know some other equations of state, like van der Waals equation of state. And an equation of state is a relation between pressure, volume, the amount of substance, and temperature in general. Sometimes this is called also the thermal equation of state. It's often not used, this word thermal, but it's used in the context when we would like to distinguish it from the second type equation of state, which is called the caloric equation of state. Or we more often use the word internal energy. It gives me the energy of our system as a function of the same variables. Here it is a function only of temperature. Volume or pressure is not present here. Well, there are other equations of states where there is also pressure present. For ideal gas, it is much simpler. And you may remember from the lectures of physical chemistry or thermodynamics that both equations of state, that is, both these formulas, whatever you call them, are needed if we proceed according to this classical picture how thermodynamics is built. So I will repeat it in few words using this scheme. Building classical thermodynamics starts with the zeroth law of thermodynamics. It says that there is a quantity called empirical temperature, which gives me the direction of heat flow between two bodies. That is, if two bodies are in thermal equilibrium, they have the same temperature, but if they are not, heat can flow from the hotter to the colder one. Now I can sit down or go to the laboratory and measure equation of state. And for example, I'll find that hydrogen is almost an ideal gas and determine this. Or I can derive it, if we have seen. It means that T is one example of the empirical temperature. It is a temperature. I don't know whether it is a good one or not. I will see this later. Also, I have the first law of thermodynamics, and it says that energy is conserved. Then I have the caloric equation of state of ideal gas. Instead of ideal gas, I can use any other substance, but it's easier for ideal gas. And from these three components, I am able to derive the equation for adiabatic expansion or compression of ideal gas. This is the ratio of the heat capacities as constant pressure to constant volume, and I know everything about this process. Then I'll postulate the principle of a heat engine. It is an engine or something that takes heat from one bath, let us say with temperature T2, converts some heat into work, and also delivers some waste heat to a bath to the second bath of temperature T1, which is lower. And if this is done reversibly, I can postulate the so-called second law of thermodynamics that says that every heat engine that works reversibly between two baths have the same efficiency. Because I can use any heat engine, I will use that one based on ideal gas. This is called the cycle of Carnot. And I will derive that for such processes the integral over the heat which is exchanged divided by this temperature T. I know that this is an empirical temperature that can be derived from a hydrogen thermometer or related to the energy. From this I will see that integral is 0, and it means that there exists a new function of state which is called entropy, and this is its definition. Since this gives me only an existence of something like this, I don't know what is the zero of the natural zero of such a quantity. We know that for volume the natural zero is that there is zero volume. It's easy, but we don't know whether there is such a natural zero for entropy yet. But according to the third law of thermodynamics, this zero really is zero for crystals at very low temperature, for ideal crystals. This is how the classical thermodynamics founded by Carnot, Gibbs, and so on works, and how a new quantity called entropy is defined. From this entropy and other quantities like internal energy, I can derive other quantities like enthalpy, Gibbs energy, and from these I can study chemical reactions, for example, equilibrium constants, and so on. So this has been the classical thermodynamics in brief. Let's proceed with the equation of state again. We wrote the equation of state of ideal gas in this form. Here we have the kinetic energy of all n molecules. This energy is composed of 3n terms, which look the same. It's the kinetic energy of in one direction of a molecule, that is 1/2 mass times velocity in one direction. Okay, this number f is called the number of degrees of freedom, or mechanical degrees of freedom, and 3 is the dimensionality of our space. It means that here the number of molecules can be rewritten as the number of degrees of freedom divided by 3, and it can be related with this formula. From this I will get the average energy per 1 degree of freedom. This is the kinetic energy divided by the number of degrees of freedom, and it is 1/2 Boltzmann constant times the absolute temperature. Note that the individual terms are different. One molecule can be very slow, one quite fast. By on average, the energy, kinetic energy per 1 degree of freedom is given by this quantity in systems which have many molecules. If we have the kinetic energy which equals the internal energy, we can calculate the heat capacity. It is defined as a partial derivative of the internal energy over temperature, in this case at constant volume. This is what we assumed. So we take this derivative using this formula, and here we have the number of degrees of freedom, which is in 1 mole. We have mole quantities, so in 1 mole it's 3 times the Avogadro constant, and by cancelling this, we'll get an important formula. That is the molar heat capacity of monoatomic ideal gas is 3/2 of the gas constant. This formula or this formula, they are equivalent, are called the equipartition principle. It says that all degrees of freedom have on average the same energy, and we have calculated this energy contribution. This formula can be extended, for example, for linear molecules. Here, in addition to 3 translation of point mass, we have 2 rotations. If a molecule is linear, we have 2 angles how to get its axis. So it's the same as we need 2 coordinates to get a position on Earth, on a sphere. It means that for linear molecules like nitrogen, instead of 3, here will be 5. There are some problems with hydrogen at very low temperatures because we need quantum mechanics. This is a classical formula. So it works only in limited cases. We must be aware of it. For nonlinear molecules like water, for example, we have 3 rotations. We need 1 degree of freedom more how to define the orientation of such a molecule in space. So then the isochoric heat capacity is 3 times the gas constant. This idea can be extended for vibrations. But the problem is that vibrations for normal molecules must be treated by quantum mechanics. So such classical expression for vibrations would be very imprecise. There is time for examples. So to calculate the isobaric heat capacity for nitrogen and for water vapor. So nitrogen is a linear molecule, so that the isochoric heat capacity is 5/2 of gas constant, and we use this formula for the isobaric heat capacity, and the total is 3.5 times the gas constant. For water vapor, the same equipartition principle predicts for the heat capacity at a constant volume 3 times R, and we must add 1 to get the heat capacity at constant pressure. It is 4R. If you calculate this, I don't have a number here, but we can do it immediately. 4 times R is oh no, we have here 3.5 times R, so sorry, is 21.10, so 29.10 for nitrogen. You can see that the accuracy is great. But for water vapor, it's a bit different. Here is the experiment. I took 2 formulas, one given by the so-called Showmate equation and the other from the engineering toolbox. There are points, and I divided the heat capacity, the molar heat capacity at a constant pressure by the gas constant. I should get 4. So at very low temperatures, or at reasonably low temperatures, it is 4 indeed, but as temperature increases, this is no longer valid because of vibrations, which cannot be treated at this level. Every branch of science has its terminology, and it's the same with statistical thermodynamics. So we must know what is a microstate. A microstate, sometimes called configuration or just a state, is an instantaneous snapshot at given time of our system that develops in time. We can describe it at two levels. We can have a quantum description. Then state is simply an eigenstate or a wave function of the system. You have heard about it, but don't care. We will not calculate anything using this concept. Just it is a name that we have states, and we can have a lot of them, but still we can number them, enumerate them. But we can also have a classical description. Then a state is composed of positions of all particles and their velocities. I have said velocities. Actually, in this business, we use for very deep reasons momenta, but for the sake of this course, you don't have to distinguish. You must understand that we need positions of all particles and their velocities to define a configuration, a state. Then we have a concept of macrostate. It's the average action of all microstates. If a microstate is this, that is individual molecules, then what I observe is a macrostate, just blue liquid instead of individual blue molecules. If the system develops in time, it goes through different microstates. Because if it develops in time, the positions of atoms change, and also their velocities are the same with the wave function. Then I can study a set of all these microstates by statistical methods. But to do that, I must know the probabilities. And if for each microstate I know its probability, which I will call pi, that boldface pi, then I say that I have an ensemble. So an ensemble is a set of all microstates, and for each microstate I know its probability. And I have a trajectory. It is a record of a microstate in time. The simplest ensemble is the microcanonical ensemble. It corresponds to an isolated system. That is, I have a system of molecules, and the number of molecules doesn't change, it is constant. The volume of the system doesn't change, and the energy is constant. There is no heat flow, no work. And I postulate the so-called ergodic hypothesis. In the quantum language, it says that probabilities of all states of the system are the same. Why this? It is something like democracy. I have many microstates or eigenstates of my Hamiltonian, and I cannot distinguish between them, or all of them are equal. So the best what I can say that they have the same probability in the ensemble of microstates. This can be expressed in a bit different way in classical mechanics. Actually, the quantum language here is a bit simpler. Just I have set a number of microstates, perhaps a huge number, but a natural number, and I can sum over them. In classical mechanics, I have a lot of trajectories, and I require that this trajectory covers the available so-called phase space with uniform probability. It is a bit problem here because I must use the correct coordinates, that is positions and momenta, so I will not use this, but I will show you only one example why it works and when this ergodic hypothesis is okay. Here you can see one particle in a box and the energy is constant, and I will show you the trajectories. So we can see that for one particle there is no chaos, it is pretty predictable. So let's take two particles. And you can see that it's pretty predictable, but these two particles once in a while hit each other, and after this collision they change their velocities quite a lot, so that there's chance that it becomes pretty chaotic. And these are only two particles. If I have 5 particles, then I can see a lot of chaos immediately. And if I have the Avogadro number of particles, certainly there should be a lot of chaos. So we can see that all these particles go through the available space essentially uniformly. But this is only an example of the space. It's what you can see are only positions. In other words, if I take a time average over a trajectory, that is, I have certain quantity x, maybe whatever, maybe pressure, maybe energy, maybe some probability that I find particles somewhere, never mind. If I take a time average over a trajectory and I take a limit of long times, that is just I integrate the system over time, take the integral of this quantity and divide it by the time, I'll get the same as is this ensemble average. And this ensemble average is written in the form of a simple arithmetic average, because all states have the same probability. So this is an equivalent expression for the so-called ergodic hypothesis. Either all states have the same probability, or the time average equals the ensemble average. And I guess one small example is useful here. Let us say that we throw dice and we play such a quite silly game that if there is number 6 points on a dice, you win $5, and if there's anything else like 1, 2 and so on, you lose $1. And the question is, what is the expected or mean win in this game? So if you play this game for a very long time with a fair dice, what will be your average win per one game? It's quite easy. I have 5 possibilities that I will lose. So I will sum up what I lose. But one possibility that I win. And I divide it by the number of states, which is 6 now. And this is 0. So this game is fair. Okay, it is possible to work with a microcanonical ensemble, and it works, but it's mathematically quite demanding. It is much easier to work with constant temperature. Actually, you remember from your course of physical chemistry that the same happens in classical thermodynamics. You started with the internal energy, and then you made several steps. You created first enthalpy, and the Helmholtz energy, and the Gibbs energy by certain operation. And for example, if we go from enthalpy to the Gibbs energy, you go from entropy is the independent variable to temperature is the independent variable, and it's easier to handle. So we'll do the same here. An ensemble with constant temperature is called the canonical ensemble. Precisely, it is an ensemble with a constant number of particles, constant volume, and constant temperature. And what does it mean that a system has a constant temperature? You should know this from thermodynamics. It means that such a system, let us say the system A here, is in a thermostat, which has certain temperature, and it doesn't fluctuate because the thermostat is supposed to be infinitely large. If we have a system in a thermostat, it means that heat can flow from the system to the thermostat and back. It means that the energy of every system, canonical system, fluctuates. It can be in the ground state, maybe 1. It may be in the first excited state, which more states, and so on. What I know from the allegoric hypothesis is that the probabilities at one energy level of all these states are the same. It means that I can write this probability of state as a function. I will use the same symbol. Pi will be a function of the energy. It is a function of the energy, and it means the probability of any of these states. Not a sum of all these probabilities, but of any of these states. And now we will use such a quite easy principle. Imagine that we throw 2 dice. The probability that one dice gives 6 points is 1/6. And the probability that if I throw 2 dice that I get both 6 is 1/36. It is the product. And this is the same here. Let the probability that I find system A at one microstate with energy level EA is this. And if I at the same time find system B at energy level EB, the probability that I find A with a state with energy EA and B with a state with energy EB is a product of these. I can write it like this. If the subsystems do not interact, the energy is a sum of them. I will assume this. That is, this product of probabilities is the probability of a sum of these 2 energies. And the only function that satisfies this functional equation is an exponential function in general. That is a constant to energy, or I can write it in this form using the x function. Here I have one number, here is the energy, and here I have the second number. For reasons that will be seen later, I wrote a minus sign here. Okay, when we think about it more, it means that if I have several systems in the same thermostat, an equation like this is true. It means that the beta depends only on the properties of the thermostat. That is, it is an empirical temperature, any measure of temperature. On the other hand, it must be satisfied that the sum of all probability is unity. That is, this alpha is just a normalizing factor. I need it so that this normalization is true. So it is just a normalizing constant, and we'll see later that it does have a good physical meaning. So I know that beta is an empirical temperature, but I don't know what is the relation of this empirical temperature to, let us say, T. It must be calculated. We can do it by using a monoatomic ideal gas. Perhaps a small note here. Sometimes it's distinguished. Ideal gas is a gas of molecules which mutually do not interact, but may be complex, may be rotating, and so on. And a perfect gas is a monoatomic ideal gas. But not always this is satisfied. That sometimes ideal and perfect gas are just phenomena. Okay, so we know the energy per one atom, and using this I will calculate the internal energy, which can be expressed as this integral. But don't worry about it, I am not going to prove it. Just you should know that using a monatomic ideal gas, I will calculate the internal energy, and on comparing it with the equipartition principle, I'll get this formula for beta. Beta is the so-called inverse temperature, and here you have also the Boltzmann constant. Okay, if you wish, here is how to calculate. What I have said, it is a bit complicated, so don't worry about it. Anyway, you have plus here, so it's just an appendix. You don't have to go through it. You can also calculate it using software if you wish, and it's pretty easy, but again, you don't use this software likely, so don't worry about it. So let's return back to the canonical ensemble. At this moment, we know that a probability of finding a system in state psi is proportional to this so-called Boltzmann factor. It's not normalized here. If we have a normalized probability, we can express the mean value, also it's called the expectation value of any quantity x, as this weighted sum. It's no longer an arithmetic average as in the microcanonical ensemble, it's a weighted sum, and this is a quantity to calculate as a function of a state, and this is a probability. So we can insert there what we know about it, and can express it, for example, like this if you wish. But if we want to get rid of this unknown alpha, then we must do two sums, because we can normalize, or we can say that the sum of this divided by the normalizing factor is unity, and we'll get the normalizing factor. So here you have the result. The result for the mean value of any quantity x, the sum over all states over configurations, is a weighted average with x multiplied by the Boltzmann factor divided by the sum of these Boltzmann factors. Let's go back to our example of a silly game with a dice. Let us say I cheat. So I'll take a drill and drill a small hole under 1, it's opposite to 6, and put a small lead there. And if I throw such a dice, I'll get number 6 with a higher probability. Let us say 0.2. And let's say for simplicity that all other points have a lower probability, 0.16. Note that this is normalized, these probabilities, so I don't have to care about this normalizing factor anymore, and let's calculate the average win. So again, I have 6 terms in total here. 5 terms give the same term. It is my loss of $1 times the probability that I lose it, and this repeats 5 times. And if I am lucky, I get number 6 points here, so I win $5, and this is the probability. And if I calculate this, I'll get 0.1. So my average win in one cheated game is 20 cents. Okay, so what we have learned? We have learned that a probability of finding a state with energy E is proportional to this Boltzmann factor. Here is certain constant, a normalizing constant. But in physical chemistry, it is often useful or common to express energetic quantities as smaller quantities. So we can put here a certain molar quantity, and then instead of the Boltzmann constant, we'll get the universal gas constant here. And I'm sure that in physical chemistry you have seen terms like this. Where you have seen such terms? Perhaps you remember the Arrhenius formula for the rate of the reaction or for the kinetic constant. It is usually written in this form, where a is a certain pre-exponential factor and we have the exponential of this kind, where this E star is the activation energy. And it corresponds to the mechanism. So if you have a reaction and the reaction coordinate and the reaction proceeds in this direction, and here there is the activation energy. So the molecule or the reactant molecules must have at least this energy so that the reaction proceeds. And we know that the ratio of these molecules that have such an energy is given by the Boltzmann factor, Boltzmann probability. Okay, there are some perhaps tiny deviations from this because it reacts also if the energy of the molecule is higher than this, but these are details. If you calculate this correctly, you'll get here a small temperature dependence, but usually this is the leading term. And the second example, I am pretty sure that you remember the Clausius-Clapeyron equation, which describes the equilibrium between liquid and its vapor. So we have liquid, we have molecules in the liquid, and we need certain energy to remove a molecule from the liquid and put it into the gas phase. So this energy can be expressed in different ways, but let us say that it's given mostly by the vaporization enthalpy. It might be the internal energy, but usually it's pretty similar. So the probability of finding a molecule in vapor should be proportional to this extra energy that I have here. This is this term. And this corresponds to the integrated Clausius-Clapeyron equation, integrated with constant vaporization enthalpy. And it's exactly what is predicted by the Boltzmann probability. So it's the Boltzmann factor, Boltzmann probability is nothing terribly new for you, I hope. And one case study, let us say, which is quite instructive, I believe. Let us say that we have gas in a gravitational field. Here I have my model in a gravitational field, which I can change if I wish here at certain temperature, and what you can see is that the gas is more diluted here up in the mountains, let us say. And at the sea level, here at the bottom, is more dense. We can measure the density profile and study it, but we'll do it theoretically. So we have a homogeneous gravitational field and a molecule of mass m there, and it means that the potential energy of such a molecule in this field is its mass times the gravitational acceleration times the height of the molecule. The probability of finding a molecule at constant temperature, of course, in real mountains it is not satisfied because there's weather and usually it's colder. Up it is a bit different model, but we'll assume the same temperature. So the probability of finding a molecule at the height h is proportional to its Boltzmann factor. I insert it here, and also I can multiply both the numerator and the denominator here by the Avogadro constant, and I'll get a useful formula. This is the molar mass of the gas. and the probability of finding a molecule of ideal gas is proportional to its density and it's proportional to pressure. So this is the final formula where P0 is the pressure at sea level at H0. Okay, it looks fine, but we have another possibility how to calculate the same result. And always, if we calculate something twice, we are happy that we understand it better. And it will be the case here. So let's assume we have a column of air, and let's calculate the difference in pressure between these two layers or levels, which are dh apart, some elementary height here. You certainly know from physics the formula for hydrostatic pressure, which is here. This is the height times the density times the acceleration, and we must understand the sign. Our height goes up from 0 and pressure goes down, so there is minus here. Okay, to integrate this we must insert the equation of state for the density, which is easy. We have it here, and we are getting a simple differential equation which can be solved easily by a separation of variables. So pressure will be put here, so is what is here, and the rest is here. Then we put integrals over both sides and integrate. Here this ratio gives logarithm, and here the integration of this element gives only h here, the height, and this is the same as this formula. And if you think a bit about this formula, you can understand the principle of multiplication of probability. This is an exponential function. The field is homogeneous. That is, if we go in levels which are of same, let us say 1 meter, always we have the probability of finding a molecule here with respect to this level multiplied by the same factor, by the same Boltzmann factor of the difference of these energies. So it is a motivation for understanding the multiplication of probability, because we go up and up, we multiply all these probabilities. And one chemical example. You know that butane has two conformations, two gauche conformations and one anti-conformation. The anti-conformation is lower in energy. I can show you butane here in the model, in molecular mechanics program, and I can also here play with the molecule a bit, do something, re-minimize, and what I'm getting is one of two gauche conformations, and it has higher energy. And my task will be to calculate the population of molecules. The population means the probability of finding, or the ratio of such molecules which are in the gauche state at the boiling point of butane, and I know the difference of energies of both states. Okay, how to solve it? First, we must realize that we have two gauche states and only one anti-state. So I can write it like that the probability of one gauche state, let us say gauche plus, is the same as gauche minus. But the ratio of probabilities of gauche to anti is given by the Boltzmann factor with delta E here. This can be easily calculated. You must convert units here, and do not forget that there are kilocalories. Here is 1 calorie, and you will get that it's approximately 0.19, this ratio. So this is one equation, the ratio of both states. And the second equation is that the sum of all probabilities is unity. That is twice the probability of a gauge state plus the probability of the anti-state is unity. Remember that you must have the number of states of the degeneracy. It's called the degeneracy of such a state or level you have here. And from this we can calculate the probabilities. We have two equations of two variables. For example, the first equation can be rewritten this way, and we can insert this by gauge here, and the result is here for the anti, and sorry, the probability of any of the gauge states is these 2 pi, that is the same as we have here, and is here numerically, and this is the result.